Imagine spending $40,000 to feed a million-page business contract to the world's most advanced artificial intelligence, only for it to forget the most critical liability clause on page 12. It doesn't tell you it forgot. Instead, it confidently invents a fake law to cover its tracks. This is the catastrophic memory barrier known as the Goldfish Problem. No matter how smart modern AI models seem, they suffer from a fundamental, architectural form of dementia. They can recognize incredibly complex patterns in the blink of an eye, but the moment you ask them to hold on to those patterns over time, their cognitive grip slips. To understand why this happens, we have to look past the marketing hype and examine the invisible ceiling of silicon intelligence. But wait, you might think, don't the newest AI models have massive context windows? Can't they process millions of words at once? That is where the industry's biggest misconception lies. Silicon Valley has sold us a massive lie about scale. They promised that if we just built larger models with bigger context windows, memory would solve itself. But they ignored the brutal physics of computing. Processing a giant prompt isn't like reading a book. It is like keeping every single word actively spinning in your head all at once. The energy and computational cost of an LLM's working memory scales quadratically. If you double the text, you quadruple the work. Worse, researcher studies show that models suffer from cognitive drift. If you hide a crucial fact in the middle of a massive prompt, the neural network suffers from a phenomenon called lost in the middle. It remembers the beginning and the end, but completely drops the center. This memory bottleneck is not a new engineering bug. It is the modern battleground of an 80-year war over how to build an artificial mind. Since the 1940s, computer science has been split into two warring factions. On one side were the symbolists. They believed artificial intelligence should be built like a massive, rigid rulebook. It used clear logic, strict definitions, and database schemas. It was incredibly precise, but it was also brittle. If a situation didn't match the rules perfectly, the machine broke. On the other side were the connectionists, who argued that intelligence should mimic the human brain using chaotic, pattern-learning neural networks. For decades, the symbolists dominated, dismissing neural networks as unscientific. But when raw computing power exploded, neural networks suddenly took over, giving us the fluid, conversational AI we have today. Yet, in their victory, connectionists realized they had built a brain with no structure. It had brilliant intuition, but absolutely no concept of hard, structured facts. To solve this, engineers had to stop treating language like letters and start treating it like physical geography. Imagine a vast, empty warehouse. If you want to organize every concept in human history, you don't use alphabetical filing cabinets. Instead, you hang them in three-dimensional space based on what they actually mean. In this warehouse, the word king floats near the ceiling. If you walk 10 steps to the left, you find queen. If you walk straight down from king, you find man. And if you walk straight down from queen, you find woman. The distance between these floating points is their exact conceptual relationship. If you measure the vector from man to king, it is the exact same distance and direction as the vector from woman to queen. This is a vector space. By translating human thoughts, images, and documents into strings of numbers, which are simply coordinate points in a high-dimensional map, we can measure the physical distance between ideas. In practice, a vector database is the custodian of this high-dimensional map. When a company wants its AI to memorize its internal knowledge, it doesn't feed the raw text directly to the AI. First, an embedding model chops the documents into smaller, bite-sized paragraphs and translates each one into a vector, a list of up to several thousand precise coordinate numbers. Standard databases are built to find exact matches, like searching for a specific customer ID number. But a vector database is built to search for proximity. It uses specialized navigation algorithms, like hierarchical navigable small world, which acts like a multi-tiered highway system. Instead of checking every single point in the database, the search engine leaps across major regional hubs first, then exits onto local roads, finding the closest neighboring concepts in a fraction of a millisecond. This architecture is the foundation of Retrieval-Augmented Generation, commonly known as RAG. To understand RAG, think of a large language model as a brilliant student taking an open book exam. Without a vector database, The student has to memorize the entire school library before walking into the classroom. This is incredibly expensive, takes months of training, and the student still gets confused and mixes up facts. With RAG, the student doesn't memorize the library at all. When you ask the student a question, the vector database instantly runs to the shelves, pulls down the exact 3 paragraphs needed to answer that specific question, and places them directly on the student's desk. The AI model doesn't have to guess or search its own chaotic memory. It simply reads the verified facts right in front of it and drafts a perfect, grounded response. But as we move deeper into the era of autonomous agents, pure vector search is hitting a quiet crisis of accuracy. The engineering reality is that vectors can sometimes be too abstract. If you search a parts database for a highly specific serial number, a vector database might return a completely different part that simply looks similar in description, failing the query. Because of this, the modern enterprise infrastructure has become a high-stakes battleground. The trend is shifting away from pure vector systems toward hybrid engines. These advanced systems run old-school keyword search and deep semantic vector search simultaneously, combining their results. They then layer this hybrid data onto knowledge graphs, highly structured maps of logical rules. This represents the ultimate peace treaty of computer science, the intuition of neural networks guided by the strict, logical rules of symbolic database systems. We are transitioning away from simple, reactive chatbots that wait for us to type a prompt. We are now building autonomous cognitive agents designed to manage entire supply chains, run complex scientific experiments, and coordinate global logistics. But an agent without long-term memory is just an engine spinning its wheels in the mud. By offloading memory to vector databases, we have given these machines a permanent, searchable subconscious. They can recall their past mistakes, reference corporate compliance guidelines from 10 years ago, and reason through entirely new challenges with mathematical grounding. The mysterious black box of AI is no longer a chaotic mystery. It is a structured map of human meaning, organized by geometry, and remembered forever.